Hey folks, how's it going? It's Mr. Murray coming to you with a video on modeling exponential relationships. Now, this is a follow-up video for my exponential models video. And in that video, what I did is we were just literally looking at, hey, I gave you a couple points. Can you plot? Can you maybe plot them if needed? But really, can you figure out the b value between them, solve for a, and come up with an exponential model? Now, that's good and all, but in the real world, reality is situations are awfully complex and way more complex than those. So I'm actually coming back to this so we can talk about it in a little bit finer detail. So, more or less, when you're working with exponential relationships, they break down into two types. The first is growth, and the second is decay. As their name suggests, growth represents something that's growing over time in an exponential way, and decay represents something that's decreasing over time or breaking down. Okay, you can think about if you have tooth decay, right? Your tooth is breaking down. So I have some examples from real life situations, and let's see if we can figure out which are growth and which are decay. Hopefully, it's pretty straightforward. So we have bacteria in a petri dish. We've got the spread of a disease. We've got money in an account. And we've got debt being paid off. If we're thinking about the interest on the debt, especially, these are generally growth examples, right? Bacteria is growing. Disease is spreading. Money in an account is increasing. Debt being paid off is somewhat, the interest is at least exponential. Right, we have radioactive waste breaking down over time. We have dating a fossil or artifact, and that is actually pretty significant because maybe we get this artifact, we find this bone, we don't know what age this is from. So maybe by using the fact that this element carbon 14 breaks down a certain amount every so many years, using that relationship and the amount of carbon present to figure out how old that fossil is. Okay, and then we have amount of medication in a patient's bloodstream. So if you currently have 500 milligrams of Tylenol in your bloodstream, that's actually a really dangerous medication if you take too much of it. It's actually really bad for you. How long until it's at a safe level in my bloodstream, right? That decreases exponentially. Remember, the big difference here when we talk about exponential growth and decay is the amount that's actually added on or subtracted depends on what's already there. So that is to say, if I look at bacteria in a petri dish, right, I'm going to add a lot more per hour if there are a lot more to begin with, or a lot more are going to die off in an hour if there are a lot more there to begin with, right? Especially in today's day and age with COVID-19, if we left it, without any kind of intervention and we just let people do whatever, right? The rate at which the disease spreads depends on how many people currently have it. The more people who have it, the faster the disease spreads. You can imagine if we had no social distancing, if we said, you know what, we're just not going to do anything, let's let everyone, whatever, keep coming to school, proceed about their daily lives as if nothing had ever happened, you can imagine how quickly we would all have gotten that disease if there was no intervention whatsoever. And then things like radioactive waste breakdown, that's really important. If you think about, we've had a number of like nuclear disasters and things like that, whether it be like Hiroshima, we had the nuclear weapons, whether it be like Fukushima, or Chernobyl, some of those like nuclear power plants that spray nuclear waste into the area, how long until that waste breaks down to a point where it's safe for humans to be around? Okay, that also depends, how much waste depends on how much is there currently. All right, so what we're going to do in this video is essentially, first I'm going to introduce you to the idea of growth and decay. And through that, we're going to try to see if we can come up with a general rule that we can use depending on if we're having a growth or a decay situation. And then from there, we're going to look through a couple of examples. Now, I do recommend for the purposes of this video and any exponential growth or decay problem, you are going to want to have access to a scientific calculator. So at the very least, if you have a graphing calculator, great, but you need a calculator that will at least be able to do exponents. In this video, you're going to see me use desmos.com/scientific. If you go to desmos.com/scientific, what that allows you to do is the operations that we're working with here, but without the need to do it with all the graphing. If you type the stuff in the graphing version, it'll also be able to calculate it for you, but I'm just saying if you want a more scaled down version without some of the graphing, this might be another option for you. But again, a calculator is going to be really important for this. Okay, so bacteria are growing at a rate of 10% an hour, right? Initially, there are 100 bacteria present. How many bacteria will there be after 24 hours? Now, this might be important. Let's say I'm a health inspector. I go in. I want to see that there's not a lot of bacteria in this food establishment, right? Because if I know the bacteria are growing potentially rapidly, and I go in there and I spot a lot of bacteria, what I know is that if these people are not taking care of their restaurant adequately, then based on how fast I know bacteria grow, if it is what it is right now, if I don't stop this, it's going to get unimaginable. And that is true about any type of bacteria or molds, right? They can be dangerous, they can make you sick, but they also grow at this exponential rate. Because if you think about it, bacteria, they engage in the reproduction with each other, right? But the amount of bacteria that can engage in the reproduction depends on how many there are there. The more bacteria, the more reproduction is possible. So here's what we know. Currently, let's say we're at time 0. So I'm going to call this time, and I'm going to call this bacteria. So at time 0, when we first start examining, there's 100 bacteria. Now, 1 hour later, we have the 100 bacteria that we started with. But we also have an additional 10% of that 100. And I'm going to represent that as 100 times 0.1, right? That's 10% of 100. Because the amount that we take the amount we had and we add an additional 10% of that. So that's equal to 100, and then 10% of 100 is 10. So it's equal to 110. I'm just going to circle the final answers. So in 2, we start with 110. And then, but here's the thing. We have to add an additional 10% of that, right? So we have the 100%, we have the 110 we started with, plus an additional 10% because it's growing at 10% per hour. So I have 110 plus 11, because if I slide that over, so I get 121. So you can see already when I had the extra 10 bacteria, right? Now I get a whole extra bacteria, right? Instead of going up by 10, now it's going up by 11. So now I'm at 121, and I'm going to take that 121 and I'm going to add to it an additional 10%. So I've got 121 plus 12.1, and that's equal to 133.1. So you can see again, now we started to go up by even a little bit more. And I can keep this process going, right? I could do 133.1 plus 133.1 times 0.1. All right, this is going to start to get pretty messy though. That's the problem. Okay, so we would get 146.41. All right, it's going to start to get right. You can see the decimal places are going to start to stack up. And this is going to get really messy. So I think we need a better way to do this. But let's see if we can figure out what we have in common. So if we look at each thing, each individual thing here, we see that each of these rows, right, we can see these things in common. And the thing is, we just learned in the quadratics, what can we do with an expression when we have two things in common? What we can do is we can factor it out. So if I take out the 100, what I have is I have 100, and then what times 100 is 100? Well, that's 1. And then if I take that away, I get 0.1. Interesting. And if I clean that up, I get 100 times 1.1. Interesting. What happens with the 110? Let's see if the same thing happens with the 110. So here, I get 110. Well, what times the 110 is 110? That's 1. What? The exact same thing. Okay, let's take a look now down at the 121. All right, this has got to be a fluke, right? So I get 121. What times 121 is 121? Well, that's 1. And then here I got the 0.1 again. So that's 121. Interesting. So notice the pattern. You're always taking the previous number and you're multiplying by 1.1. Okay. And that makes sense because at every step, at every hour, you always have 100% of what you started with plus an additional 10%. The extra 10% that you're growing every hour. Now, here's the other thing I noticed. 110. Well, isn't 110? Let's just take this because I just want to think about this real quick. This is just something that just occurred to me as I was really kind of writing everything out and really taking the time to think about things. So let's go down here and take a look. So first, what we had is we started with 100. And then what we did is we did 100 times 1 plus 0.1. And we said, okay, well, that's 100 times 1.1. And that's 110. And then what we did, well, we did 110 times 1 plus 0.1. And we said, all right, well, okay, that was 110 times 1.1. And right, we said that was 121. Okay, and then we did 121. Okay. Okay, 121, and then for 121, we got what? 133.1. Okay. Now look, I just noticed something though. Look, 110 is the same thing as 100 times 1.1, is it not? So what if I took this and I turned it on its head? Look, 110 is equal to 100 times 1.1. And now I bring in that original 1.1. Right? And remember, this is month 0, this is month 1, this is month 2, this is month 3. Just keep that in mind. What happens though? What just happens here? I have 100 times 1.1 times 1.1, and that's 100 times 1.1 squared. And so notice in month 2, I get 100 times 1.1 squared. Let's look at month 3. Now, 121, wait a minute, 121, well, we just figured out what that was, 100, right? Because 121 is the same thing as 100 times 1.1 squared, right? The whole point is we just rewrote this. So when I'm trying to find step 3, instead of writing 121, I'll write 100 times 1.1 squared, right? Because we know that's the same thing as 121. And I bring my 1.1 in again. And now what do I get? 100 times 1.1 cubed. And notice it's the third month. So this is interesting here. So things I see. 1, what's the significance of the 100? The 100 represents what? The initial value. So I can see the initial value in my equation here, and then my 1.1 representing the 100% that I start with each month, and then the plus representing the growth, and the 0.1 representing the percent of growth, which is 10%. Okay, let's go ahead and look at an example with decay. So currently there are 250 milligrams of a drug in a patient's bloodstream. Each hour, the amount remaining in the bloodstream is reduced by 25%. It will not be safe to administer more medication until there are 10 milligrams or less remaining in the bloodstream. If it is 8 a.m. now, at what hour of the day will it definitely be safe to administer another dose to the patient? So folks, this is like life or death stuff. Imagine if you were to administer a medication to a patient, having too much of that medication in their bloodstream could be extremely life-threatening, depending on what medication that is. So what we do is we have an exponential relationship that will help us figure out what time it will be safe. So it will let us, 1, effectively treat the patient, but also not endanger their health. Okay, so, and if you think about it, if we think about it like that, maybe if we're the drug manufacturer, that's when we, release our guidance to the doctor. So if you ever have if a doctor's ever written you a prescription, take this medication every X number of hours, or once per day, or twice per day, that might be based on how safe it is to have X number of milligrams in your bloodstream. So let's take a look. At hour 0, we have 250 milligrams of this drug in our bloodstream. Now, after 1 hour, right, we have the original 250 milligrams, but then we've subtracted out 25% of that 250, right? Because we've lost 25% of the drug that's in our system. Okay? So that is 250 minus 62.5. And that is 187.5 milligrams. So after 1 hour, that is how much is currently remaining. So then if we think about after 2 hours, we'd have the 187.5 that we started with, minus 25% of what's currently in the bloodstream, right? The amount remaining is reduced by 25%. And this, right now, happens to be the amount remaining. So when we do it like this, and if we can calculate it, 187.5, if we take a quarter of 187.5, it is not nice at all. Because since this has 1 decimal place and this has 2 decimal places, right, it really makes things nasty. As it turns out, it's 187.5 minus, get ready for this, 46.875. And when we do that out, what we get is 140.63. And this is already really not good. I already really don't like this, and I know by the time I get to 3, I'm not going to want to deal with these decimals. So already I want to find another way. So to do that, let's take a look at what we got here. We're going to use the distributive property in the same way. Because notice at this point, if I use the distributive property in reverse, if I factor out the common factor, I have 250. Then what times 250 is 250? Well, it's 1. What times 250, what happens here? Well, what I get is minus 0.25. So what, as it turns out, it looks like the same thing, except instead of 1 plus, we have 1 minus. But look, this is equal to 187.5. And by the way, that makes sense. 0.75. Because think about it like this. If you take 25% off something, there's 75% remaining. So if you go to the store and you want to calculate, oh, there's a 20% off sale, you could think about that as finding out what's 80%. Because if you take 20% away, there's 80% remaining. Similarly, if 25% of the drug is gone from the patient's bloodstream, then 75% remains. Now, we know that 250 times 0.75 is 187.5. So in this step, when we write the 187.5 times 0.75, remember we can take it a step further. Because 187.5 is 250 times 0.75. And then this 0.75 comes down. So notice it's really 250 times 0.75 squared. And so just like exponential growth with this exponential decay, right, you also have this similar notion regarding your powers here. Okay, so in the end, we could continue with this going. Using my calculator, right, I could continue to plug in and plug in and plug in. And what I'll find is that if you plug in 12, right, once you get your function, if you plug in 12, that will get you your first time a whole hour where it's below 10. And so we would interpret that to mean 8 p.m. since we started at 8 a.m. Okay, so these are the kinds of questions that are real life, and in this case, literally life or death situations that involve exponential growth and decay. So in general, any exponential growth model, there's a few different ways you'll see it written. Okay, sometimes you'll see n, sometimes people will also use t. There's a lot of kind of complicated exponential growth and decay models. So sometimes you'll see it written like this, f of n. Now, this is growth, so we start with the original amount, as we saw before. We do 1 plus r to the power of n. And again, sometimes people also write it like this. F of t equals a times 1 plus r to the power of t, where t represents the number of whatever, right? So this means the period, when you think about the periods just means like how many years have gone by, how many months have gone by, how many days have gone by. Okay, so either one of these means the exact same thing. It's just different lettering. Eventually where we're going to go with this is more complicated exponential growth. For example, when I give you a yearly rate, but the growth is actually being done more than once per year, like what you guys saw with the Exploration Google spreadsheet where we talked about paying off debt. That's a situation that's a little bit more complicated than this. Exponential decay is going to follow this model. F of n, so here's the difference. This is going to be a, and now instead of plus, we're going to do minus r to the power of n, or sometimes people write it with the t. Remember, it doesn't matter which version you use, but do be on, kind of be on the lookout for any context clues in the problems or directions as to what version you might want to use. Okay, so notice the main difference is the plus versus the minus. Growing, you're adding. Decay, you're taking away. What symbol do we associate with adding? Plus. What symbol do you associate with taking away? Minus. If you're adding, you should be having more than 100% of what you started with each period. 1 plus will ensure more than 100%. If you're decaying, you should have less than 100% of what you started with each period, and that is what is happening here. So coming up, what we're going to have is some problems for me to do, for us to do, and for you to do. So stay tuned, because I think this is going to be really important in continuing to kind of develop our knowledge around exponential growth and decay. Okay. So here we go, and as you can see here, I'm using my Desmos scientific calculator because this is really all I'm going to need to be able to do this problem. So this will be one for me to do. So the value of a collectible baseball card is increasing at a rate of 0.5% per year. In 2000, the card was worth $1,350. Find the value of the card in 2013. So this is basically just picking out the important information and setting up an equation. It's not too interesting in that regard. So remember, everything is going to look like this. First of all, it's increasing. So let's let T be the number of years since 2000. So then f of t is equal to the initial value in 2000 plus 1, and then times rather 1 plus, because it's increasing, r to the t. Okay, and we know that in the beginning it was $1,350, and then each year it's going to grow by 0.5%. So here's what I'm going to say to you now. The trickiest part, I believe, of this is going to be that not choosing the correct value for r and not converting to decimals correctly. Remember that you're often going to be given a percent, but you cannot plug a percent as is into an equation. You must make it a decimal. So to help you remember to make it a decimal, you see you have the percent sign. Don't forget what that means, right? Percent means per out of cent, 100. Century, right, has 100 years. A cent is 1/100th of a dollar. You got to remember to convert percents to decimals. And I'll show you what difference it's going to make, because if you don't do that, you're going to get this function instead. And what I'm going to do real quick is, and I'm as much a Hank Aaron fan as anyone, except a real diehard baseball fan probably will like Hank Aaron more than me. Just going to box that out. And I'm going to show you the incorrect one. So if we had done 13, so I'll show you that it will make a big difference. So sometimes people do it like this. They just take the percentage that they see and they plug it in wholesale. So let's see how much of a difference it makes. So on the correct side, I've got 1.005 to the power of t. And on the incorrect side, I've got 1.5 to the power of t. Now, in 2013, how many years has it been? It's been 13 years. So here's what happens, right? In year 0, we would get 1 for our thing because we're doing to the power of 0. So in year 0, we were at 1350. In year 1, we've multiplied by 1.005 once. But by year 2, we multiplied by it again. And then we multiply by it again, right? So all we're doing is we're taking 1350 and we're multiplying by 1.005 to add that 0.5% 13 times. And when you multiply something over and over by itself 13 times, that's doing to the power of 13. So we get, let's go ahead and access our smart notebook calculator here on Desmos. So you got 1350 times, open your parenthesis, 1.005, close your parenthesis, to the power of 13. What I get is $1,440.43. Correct answer. Now, if you think about it, 0.5%, half of 1%, not a strong amount of growth. If you think about it, think about to you what represents a lot of growth. 100% is literally doubling. That's a really high level of growth. Even growing by 1% is a relatively large amount, but 0.5 is a very, very small percent of growth, 0.5%. Let's see what happens if I use this answer here. So if I had done the 1.5, the idea of multiplying over and over by 13, that doesn't, or rather by 1.5 and having an exponent of 13, that doesn't change anything. So let's see what happens if I now come in here and I do one simple change, and that is that I take the 1.005, notice the first deletion, the second deletion. So this says my card, if I'm not mistaken, just by switching it to that, is worth $262,736.33. And you got to ask yourself, if something is growing at a rate of 0.5% per year, could it reach $200,000 from only $1,000 in 13 years? That is not realistic. So the tricky thing here is you've got to look at your work and you've got to ask yourself, does this answer make sense? And if it doesn't, you have to go back and take another look at your formulas. Okay, so this is not right. This is the answer we want. We don't want any of this. All right, here's another little example, and in this case, I do have my Desmos calculator available, and I'm also going to be trying to do a graph as well. So here we have an exponential decay. So a house is losing value at a rate of 5.4% per year. In 2009, the house was worth $131,000. Find the worth of the house in 2019. So the house is losing value. So every year, it's got 100% of its value minus 5.4% of that value because it is losing 5.4%. So if you think about it, let's say I start at 131,000. If I lose 5%, how much percent remains? The answer is 94.6%, right? If you take 100% and you take 5.4% away, what remains is 94.6%. And that happens to be 1 minus 0.054. Okay? You can check it for yourself. And so my function that I want is f of t equals 131,000 times 0.946 to the power of t, where t equals years since 2009. So in this case, this is a tough graph to work with. So this is 1530, 40. So this looks like it's going up by 150, or rather 15,000s. So it looks like I'm somewhere around here. I'll see what happens. So here's what we've got. This actually doesn't go all the way up to 2019. So let's take a look. So I've got 100, and I got to remember that I got to get off pen mode. Sometimes I forget to get off pen mode. So here we go. 131,000 times 0.946 to the power of 1. So if I do that, that tells me after year 1, I'm at 123,926. So here I am. And that's going to be tough to graph. We'll see what we got. Okay, now I'll come back in here and I'll switch to 2. So now I'm at 117,233. So this is 105. So again, really difficult to necessarily graph this. You can see the rate is pretty slow here, and that's because we're losing only 5% per year, but it does add up over time, right? You can see it's like got a slight curve to it. Let's do 3. So now we're back to 110. So we're just a little bit over there, and it's going to continue to go like that. What's going to happen after 10 years? So for basically 2019, we want f, that's going to be f of 10. So f of 10 equals 131,000 times 0.946 to the power of 10. And what we get, as you can see here, is approximately 75,193.91. I'm going to round to 2 decimal places because it's money, and money typically rounds to 2 decimal places. So it loses value. And then if you think about it, right, if we keep this house going and we don't do something and turn this house around, right, 20 years later, you're going to have 43,000, right? You're not going to have much to leave it there. So it's not a very good investment as in terms of how a house would be. Right? So given that we have these two major functions here, so we have our exponential growth function, a times 1 plus r to the n, or a times 1 plus r to the t, and our exponential decay, a times 1 minus r to the n, or 1 minus r to the t. Here's what I want you to do. I want you to take a moment, and I want you to use Desmos or some other graphing calculator, whatever you have access to, maybe your own graphing calculator. For each of these situations, for the first two, write an exponential growth function. I'm going to say for right now, let's also determine the domain and range if we can, and then find the value of the function after the given amount of time. In the first two, we're going to do that with growth. In the 3 and 4, we're going to do that with decay. So again, pause the video, find the growth or decay function, the domain and range, and the value after the given period of time. Then when you're ready, unpause, and you can see what I got. Cool. So here we go. Basically, what I got here is we're starting at 650,000, so I'll put my 650 in. 2, 3, 4, 5, 6. Then we're growing at a rate of 4% per year. So growing, every year we have 100% of what we started with plus an additional 4%. So we have 650,000 times 1.04 to the n. Now, what's the domain of this function? Well, given that the time period has to be at least 0, the domain in essence is 0, bracket included, to infinity. And I say that because you cannot have negative years. So from a practical point, you have to have a domain of 0 to infinity, and the range, well, we start at 650,000, and really the sky's the limit to infinity. Okay, after 5 years, we plug in 5 for n. So in my calculator, I'm going to do 650,000 times 1.04 to the power of 5. And what I get after 5 years is 790,824.39. So it's a pretty significant increase. In only 5 years, you're making almost 150,000 more per year. It's pretty significant. That's a lot of money. This is an important one here, and this is something we think about a lot at Milton High School. How do we plan for the future? How do we, when we're building a new building, how do we think about, well, we need to take care of these Milton High School students we have now. But look, and the reality is this building needs to last for a while. And the reality is in 10 years, there's going to be more students than there are now. The population of this school is 800 and is increasing at a rate of 2% per year. So let's see if we can figure out what the exponential function will look like. So here, by the way, you ought to write f of n. Here I'm going to write f of n equals 800 times 1.02 to the n, because I've got my 1 plus the 2%. Okay? The domain is again 0 to infinity, 0 included. The range is 800, because it's at least 800 now, to infinity. In our function, because given the fact that 0 is the smallest input because we can't have negative time, I would interpret that to mean that 800 is going to be, and 800 has got to be the smallest output, right? Because if it's only growing, it's not going to be any less than 800. Okay, so for 6 years, we plug in 6. So I do 800 times 1.02 to the 6. I'm going to show you what that looks like. And I'm just going to swing back to this previous page real quick. So you should get 800 drats. You should get 800 times 1.02 close power 6, 900.9299. And you can't have 9.92 of a person. So I'm going to say I would plan for there to be approximately 900 students. So that's interesting, right? Because if I build a school, think about it like this. Imagine I build a new Milton High School. And I know that I need 800 kids. Now, by the time the freshmen graduate, I'm going to be creeping up on 100 more kids. So I need to make sure my building is going to be able to accommodate that. Now, here's the reality. What would it look like in 20 years? Take a guess. What do you think it would look like in 20 years? Almost, I'll tell you, 1,200 kids. So what that means is that there's going to be an almost 50% increase in the number of students over 20 years. So if you're building a building, think about that. In 20 years, if you put it into perspective, we're coming up soon in the next 5 to 10 years where Milton High School, the one that we are in now, will have opened 20 years ago. So think about that, okay? That's pretty significant. Write an exponential decay function to model these situations. So now we're going to do decay. So remember, with decay, we should be doing 1 minus. So we have a population 2,500 and decreasing at a rate of 3% per year. So I've got 2,500 now. And then every year I have 1 minus 3%. The 100% I started with minus 3% of that. So it's going to be 2,500 times 0.97, and that's right in our function notation. And now we need to know after 5 years, so I plug that in, 2,500 times 0.97, close my parentheses, and do to the power of 5, and I get 2,146.8, so I'm going to say 2,147 because we're talking about people. Okay, domain. I'm going to say 0 to infinity on my domain. 0 included. Range. Here we got to be careful. So we're going to most likely have more than 0 people in the town. And then the most we're going to have is 2,500. So this domain's a little bit different because you have, first of all, the fact that people need to be at least positive. But now because you're decaying from 2,500, you need to remember that you're now going to have at most 2,500. So it's a little bit different than some of the range situations versus where revenue, the sky's the limit. For population, there's no end. People could keep coming in and coming in and coming in forever. All right. Finally, the value of a company's equipment is $25K, decreased at a rate of 15% per year. Okay, this is what we call depreciation. So a company wants to think about that when they're considering their expenses. So we start with 25,000, and if we lose 15% per year rather, we have 18% remaining. So here's our function. The domain is 0 to infinity. and the range is 0. And technically, we could have the value be worthless. We can debate what kind of bracket there, but undebatable, the most we could have would be 25,000. And these actually, now that I think about it, please make sure these are both bracketed, because 0 will actually yield an answer of 25,000. So we should bracket that. Now, after 8 years, we just plug in 8. So we do 25,000 times 0.85 to the power of 8, and I get $6,812.26. So that's all we're doing, right? We're just essentially setting up some exponential decay models, plugging in, and growth models, plugging in, and seeing what we get. Please make sure, if you need to, you do rewind to make sense of this, as in a moment I am going to go ahead and continue on. Okay. So now we got Odette. This is a little bit more challenging, so let's do this one together. Odette has 2 investments that she purchases at the same time. So first she's got investment 1 here. And investment 1, she had to pay $10,000 to get in on investment 1. And she's going to get herself 4% per year. This might be a little bit more secure with a little bit higher guarantee of income. We could talk about investments all day, but the idea is the riskier the investment, the more you stand to gain, but also the more you stand to lose. So maybe she wanted to keep her money safe. She put $10,000 in, but she's only going to get 4% per year. That's actually still very, very good. On the other hand, now she goes for investment 2. Now investment 2 is going to cost $8,000 and earn 6% per year. So less investment to start, but a little bit more interest earned. First, let's write exponential growth functions that can be used to model the values after t years. So remember, v1 of t, we start with 10,000, and then what goes in here? 1.04 to the t. Then v2 of t equals initial 8,000 times 1 point, let's look at the rate, 0.06 to the t. Perfect. Now, find the value of each investment after 2 years. And we need to explain why there's a significant drop in the difference between their values. So in other words, when we started, there was a $2,000 gap in how much each one of them was worth. Now, the reality is the red function is growing faster than the blue function. Apologies. The red function is growing faster than the blue function. So what that means is that its value is going to be increasing more rapidly as the months go on, meaning that after a certain period of time, it actually should end up being worth more. We'll see if that actually happens. So now, here's what we're going to do. So to get after 5 years, let's start with the first function. So v1 of 5 equals 10,000 times 1.04 to the 5. I'm going to do that on my handy dandy graphing calc. When I do that on my graphing calc, I get about 12,166 and 53 cents. And now when we do v2 of 5, we get 8,000 times 1.06 to the 5. So we do 8,000 times 1.06 to the 5. And now what we have is approximately $10,705.80. So what I'm going to do is I'm going to take these last two and I'm going to actually take the difference of them. So do my 12,166. I'll take the difference. So now, interestingly, I wouldn't know if it's significantly less, but now it's worth noting the difference is about, if I do 12166.53, even if I do just the raw numbers, I get $1,460.73 based on how I've rounded it. Okay? So the difference has decreased, right? Now, instead of being a $2,000 difference, there's only a difference of about $1,461. And again, that's because one is growing faster than the other. If we were to continue this, let's take a guess. What if we do, I don't know, just for time's sake, let's try 10 and 10. V1 of 10, V2 of 10. So first, I'll just go back using my calculator and plug 10. I'm just literally plugging in numbers. So if I plug 10, I get 14,802.44. And if I plug 10 into the 8,001, I get 14,326.78. So this is a pretty good sign one's going to overtake the other. Let's go for 11. Ooh, 11's pretty close. It's only about a couple $100 off. What about 12? Yep, so if you plug in 12 to V1, what you get is $16,010.32. But if you plug it into V2, you get 16,097.57. Okay? So after 12 years, one will exceed the other. And we don't know what year the investment actually began, so we can't give a specific year in time. Okay, but all we're doing here is we're applying the idea of exponential growth. Okay, last two questions, and I want us to consider this. So a car depreciates in value by 20% each year. Graham argued that the value of the car after 5 years must be nothing, since 20% times 5% equals 100%. Do you disagree or agree? Explain fully. So this is one of the most common mistakes that people make, and actually this is a mistake that people like stores count on you to make to get you to come in so they can sell you extra stuff. Sometimes they'll say, take an additional half off our half off deals. So what you think is, oh, I save 50% and another 50%, so things are free. But here's the thing. That's not true. So what you're doing is you're not taking 20% off the initial value. So let's say my car starts being worth $10,000. Once I take 20% off, that's my amount after the first year. But after the second year, I'm not taking 20% off the 10,000. I'm taking 20% off what's remaining of that. And then after that, I'm not taking off the original. I'm taking off what's remaining. And so on. And so on. So what I'm really doing, right, is doing 10,000, for example, in this case, times. Now, if it's depreciating by 20%, what I really need to have is 80%. Apologies. So I get 80% to the power of 5. And if we actually see what that looks like, that is like multiplying 10,000 by 0.3278. So in other words, your car has lost not actually 100%, but it has lost a pretty significant percent. So it's lost 67.22%. So it's lost about 2/3 of its value. And there's a lot of truth to that. Cars actually do depreciate pretty significantly. But the moral of the story is percents do not add like that. So you've got to be very careful. Workers at a plant, and I liked number 6 because this is really relevant to now, and it's a really important social justice issue. So workers at a plant suffered pay cuts of 10% during a recession. When the economy returned to normal, their salaries were raised by 10%. Should the workers be satisfied? Now, this is something that often happens because companies during a recession, like we may be encountering due to the COVID-19, have to cut pay, because if they don't, they're not going to have enough money to be able to stay in business. However, it's what's going to happen after they get over that hump that we want to make sure that we're kind of paying attention to. As it turns out, the workers should not be satisfied, and I'll tell you why. This is actually really a trick to trick them. You can't just take 10% out and put 10% back, because when you raise the 10%, that 10% is based on that reduced salary. So here's an example. Let's say I was making the minimum wage of $15 an hour. Depending on what state you worked in, it might be $15 an hour. If I have my pay cut by 10%, then only 90% of that 15 remains. So what I have left is I'm now making $13.50 an hour. Here's the problem. When the economy bounces back and I add my 10% is not based on the 15. My 10% is based on the $13.50. So here, whereas I multiply by 0.9, here I'm going to multiply by 1.1, because I want to have 100% of the $13.50 plus an additional 10%, and I'm actually back at $14.85. Does 15 cents seem like a big deal? Now, if it's an hourly rate, your average employer works 40 hours a week for 50 weeks a year, and you have 1,000 employees. So again, if you pay each employee 15 cents an hour less, they work 40 hours a week, 50 weeks a year, and you have 1,000 employees, this 15 cents actually saves your company $300,000 just by paying that salary raise in this way. But you can see that this is definitely not fair. And what's even more unfair is the idea that you might trick your employees into believing that taking 10% and then giving back 10% makes everything even. The truth is, it actually does not. So hopefully you found this video to be helpful. I really appreciate you taking the time to stick through it. This is definitely not an easy topic, and that's why we're going to spend a couple days working through it. Thanks again, though, for tuning in. Feel free to send questions my way. Best of luck. Don't forget to love math, especially this really, really cool and important stuff. And remember, you can do it. Until next time, have a great day.